I'm just going to look at an alternative way of doing integration by parts. You see it uses a table format to do it. First column is differentiation, second column is integration, and the third one is curiously labelled plus minus. How does it work? Remember, we know integration by parts is the integral of u to v, which I've just written on the first line there. So how I get my answer? See what I've done? So the question is written there, u to v. So you've still got to work out what's going to be u, what's going to be dv. But we write it in the appropriate columns. I actually integrate the dv and get v for the first step, and we go uv plus. So I've got uv down there. The next thing I do is I keep doing what the column says to do. So u I differentiate, now v I integrate. You'll notice this has changed to a minus because now the same pattern, minus integral v du. So that's the idea behind it. It can get useful when you have to keep repeatedly doing it because you can just keep filling in the column and keep following the pattern. So u is still no different. You know, choose it so the differentiation makes it a simpler function, and dv still choose it so it's something you can integrate. So there's some cases here because it's another one of these methods that sometimes gets showed to people for a specific type of question. I always think those sort of methods, well, they're very limited. Surely we should be able to use the technique for every type of question. So I might go through a few cases here to show you that actually you can use it for the other. Now whether it's smart to use it for all the cases is a different question. But a polynomial times something that can be integrated. We will end up differentiating the polynomial down to 0. So here's integral of x cos x. Set up the table, first row goes the question. In this case it's the x I'm going to differentiate, the cos x I'm going to integrate. Down in this column, well, the first line's blank, but then I go plus, minus, and if I get more rows, I'll go plus, minus, and so on. Sometimes called the method tic-tac-toe. So I fill in my differentiation until I go down to 0, because it's a polynomial. So eventually we will get 0. And then I integrate in the other column and just level it out. Okay, so here's our answer. Tic-tac-toe, x sine x. Tic-tac-toe. Minus cos x, and I don't need to do the next one because I'm going to be 0 times something, so I know I've finished, and there's my answer, x sine x plus cos x. Try that one, x squared e to the x. So in each case, this one, it's the polynomial I'm choosing for the differentiation because I'm going to keep differentiating till I get to 0. So I start at x squared, differentiate 2x2, I'm down to 0. The other column, well, that's nice and easy. Integrate e to the x, e to the x, e to the x, e to the x. All right, now for our answer. Tic-tac-toe, x squared e to the x. Tic-tac-toe, minus 2x e to the x. Tic-tac-toe, plus 2e to the x. There's our answer. What if we end up with a polynomial times something that can't be integrated, though? Well, then I'll still use this method, but obviously I can't use the polynomial now to be the thing I'm going to keep differentiating. So it's going to be the other one. So when do I stop? I stop when the product of the line, if I look at the line, and the product of that line is integratable. So let's just do it with our log x. Set it up. So log x is the one. We'll keep going until the product of the line is something we can integrate. At this stage, it's not because that's the question, log x, we can't integrate it. So let's look at the next line. 1 on x times x is 1. I can integrate that. Tic-tac-toe, x log x. Oh, hang on, when I go tic-tac-toe here, what's going to happen? Because I've got nothing on that line. But the next thing is minus, so it's minus 1 dx. Which is x plus c, minus 1. Why minus 1? Well, let's look at the next example and see if we can pick up on the pattern. So if I want to do inverse tan of x, differentiate. I've got 1 on 1x squared times x. That would be differentiable. Tic-tac-toe, x inverse tan x, minus x on 1 plus x squared. Can you now see what the minus is that I've written down? Remember I said we stop until the product of the line is integratable. That's what I'm writing down, the product of the line that I stopped at. In the first one, x times 1 on x was 1. So that's what I integrate. In this one, the product of the line is x times 1 plus x squared. So that's what I write down. The sign underneath is the important bit, whether I go minus or plus, depending on when I stop. Oh, there's my final answer, of course. So let's try it on this one then. X cubed log x. I will keep going until the line can be integrated. So 1 on x, a quarter, x to the power of 4. Now, if I was to multiply those two things together, could I integrate them? Yeah, I could. It's just a polynomial. Okay. Tic-tac-toe minus the integral of that line. So a quarter, the integral of x cubed, which is minus the 16th x to the 4. Of course, the other way I could have done this one, because whilst we said we can't integrate log, actually we can. Because if you recall, the integral of log is, of course, x log x minus x. So using the tic-tac-toe method, tic-tac-toe minus, product of that line, which theoretically is integratable because we know how to integrate log x, and eventually you do get it. As I say, not suggesting that's a good way to go on that one, but you can do it that way if you wanted to. What about both of the functions can be integrated and we've got a choice? Stop when the product of the line is integratable or a multiple of another line. E to the x cos x. Okay, I'll go this way. E to the x cos x. Differentiate, integrate, I've got e to the x sin x. So no, I still can't integrate it and it's not a multiple of another line. Do it again. Tic-tac-toe, next line. E to the x minus cos x. It is now a multiple of a previous line. So tic-tac-toe for that bit, but now I'll go plus the integral of that multiple of the previous line, which I can move to the other side and divide by 2. There's the answer. Some other ones. That dx is not meant to be in the power. Okay. X e to the x dx. Okay, x e to the x. So this one, let's differentiate it down till I get 0. Integrate the other one. Tic-tac-toe. Tic-tac-toe. There's the answer. X e to the x minus e to the x. Okay. Inverse sine x. Okay, differentiate inverse sine x. I get 1 on the square root of 1 minus x squared. X times that, yes, I could integrate x on that. So we'll go tic-tac-toe, but then it will be minus the integral of the product that we stopped at. And that one there will end up being a du on root u. Well, I've got to play around with the coefficient, but eventually we'd get x inverse sine x plus root 1 minus x squared plus a constant. Okay, let's have a look at this. Square root of 1 minus x squared all over x squared. How would I have done it? There's my two functions. I've split it up into the two things. Now, have I got something that can be integrated? Yeah, the x's would cancel. I'll end up with 1 on the square root of 1 minus x squared. That's an inverse sine, so I could do that one. So tic-tac-toe minus the integral of the product of that line, and we have our final answer. This is not the integration by parts method. This is just another thing. Now remember, e to the iota theta is equal to cos theta plus I sine theta. 2020 extension 2 HSC question. Show that for any integer, this expression. It's our standard expression. So all right, we write it out. I've expanded it all. There it is. But then we play around with odd and even functions, and we get some cancelling, and we get 2 cos n theta. That was the first part of the question. Not too bad. Hopefully we pick up the marks for that. It's a pretty standard sort of result. By expanding this expression, so we're going to remember our binomial theorem idea, show that. Okay, expand it out, coefficients go 1, 4, 6, 4, 1. Tidying up those powers, and you'll notice how I've grouped them. I've got the 4 iota theta and the minus 4 iota theta together, and the 2 iota theta, because now I can go back and sub in cos, or 2 cos I should say. I can sub in 2 cos, well, 4 theta for the first one, 2 theta for the second one. And now I should be able to play around with this and get the result that they want. Now what on earth has that got to do with integration? Because part 3, hence or otherwise, they do say otherwise, so of course you could use a completely different method if you wanted to. Find this integral. Well, I now know cos to the power of 4 theta would be 1/8 this expression. I can integrate each bit of that, sub in, Beautiful thing about subbing in pi on 2 with sine is that when it's an even multiple, it's always going to give me 0. So I just have 3 pi on 2, or well, an eighth of 3 pi on 2, 3 pi on 16. Now, I'm going to show you how, sorry, that was an HSC question where they used Euler's. But it does bring up something like this. E to the x cos x. Well, I could say that actually is the real part of e to the x cos x plus I sin x. But hang on, cos x plus I sin x, that's e to the ix. So now, all I've got to do is integrate e to the power of 1 plus ix. It's still integration. It's an exponential. I'll do the same thing as I always do. Well, it'll be 1 over the coefficient of x, so that's 1 on 1 plus I, e to the 1 plus ix. I got a half, because 1 on 1 plus I becomes 1 minus I over 2. Pulled that out. I got a half of the real part of 1 minus I, e to the 1 plus ix. But hang on, e to the 1 plus ix, that'll end up being cos x plus I sin x, remember? Right up the top there. That's what I substituted in. But I want the real part of that. Oh, okay. So I end up with half e to the x cos x plus sin x, and there's the answer to that integral. By the way, I'm not suggesting you would do it that way. But it is interesting to look at. You could use your complex numbers instead of using integration by parts with that one.